Compound interest calculations. The formula to calculate compound interest is a little bit more complicated than the simple interest formula because it relies on the number of times per year that interest is compounded. And the variable that we're going to use for that number of times per year is lowercase n. So the formula for the total amount of an investment after earning compound interest, the total amount, this is going to be represented as capital A, is A equals the principal times a bracket 1 plus the interest rate divided by the number of times the investment is compounded, all of which, everything in the brackets, raised to the power of the number of times that it's compounded each year, times time, the length of the investment. So that is our formula for calculating compound interest. And in this case, it's in the simple interest case, our formula was to calculate the interest I. In this case, we're calculating the total that the investment is worth, which is the principal plus the interest that's been earned. And we call this A. I'm going to try to give you some examples which have really plausible values in them. So that you can start to get a sense of how much money individuals can expect to make on some pretty reasonable investments. So for example, for their newborn child, parents deposit $10,000 in a college account. So that's our principal. That pays 4% interest. So that's R, 0.04, compounded annually. So annual compounding means the number of times that is compounded each year is just 1. How much will be in the account on the child's 17th birthday? So that means we're going from newborn, which is age 0 really, to 17. So that's 17 years of growth in this account. So we want to know how much interest did the parents earn. So we're going to start by calculating A equals P times 1 plus R over N, all to the power of NT. And we'll go ahead and calculate this amount that's in the account. So P is 10,000 times 1 plus R is 0.04. N is just 1. And again, N is just 1 times 17. And we're going to throw this into our calculator. The way I would do that, if you have a scientific calculator that you're comfortable with, you can just type that long expression in. Just be careful when you're typing in the exponent that you type. You usually use like this caret symbol, and you might want to try to type like, in this case, you don't really have to type 1 times 17. You could just type 17. But I often try to put that exponent in brackets, so that if there is a multiplication in there, it all gets used in the exponent. You have to be careful with your scientific calculator and making sure that the order of everything is correct. And so it's a really good idea to check that you can get the same answer for these calculations as you go along, so that you're comfortable using your calculator. And if you find that you're getting different answers trying to calculate the same thing, that you reach out and figure out what it is, what's the problem with how you're typing it in, so that you can make sure you're doing it correctly in the future. Anyway, I just typed all of this into my calculator, and what I get is that at the end of 17 years, this investment is worth $19,479, and rounding brings me to 0 cents. So how much interest did the parents earn? Well, I would be equal to the total amount minus the principal, which in this case would be $19,479 minus the initial $10,000. So the interest earned is $9,479. That's pretty significant. You're talking about, making an investment of $10,000, basically doubling over the course of 17 years. And 17 years is a long time. But you can start to see the power of investing early for certain goals. So what if these same parents made the same investment, only it was compounded monthly? Well, A would be $1,000, or $10,000, sorry, times 1 plus. R is the same, 4%, only N is now equal to 12. Compounded monthly means that we're compounding 12 times per year, which means that we get 12 in the exponent, we get 12 times 17. And again, this is important when you're typing this into your calculator. If you use that, every calculator can be a little bit different, but that you make sure that you capture 12 times 17 in the exponent, and you get that all in correctly. Well, if I do this, then that total amount is equal to $19,716.47, which means that the interest would be that minus 10,000, so $9,716.47. So again, we've sort of seen that earlier, that how often it's compounded doesn't make a huge difference to the amount you earn, at least compared to simple interest. But the more compounding, the better. However, it's not as significant. And as you'll see in future examples, this interest rate can play a much bigger role in the amount an investment earns than monthly compounding versus yearly compounding. Another example here, Meghan is calculating how much she needs to invest for retirement. She's going to invest in a mutual fund that should earn her, and mutual funds are investments in stocks and bonds, and they're managed portfolios of investments. So they're not guaranteed to make 6%. But let's say that she has some trust in this mutual fund she's done her research. She expects that it should be able to earn her 6% compounded annually. How much does she need to invest to have $100,000 in her account after 15 years? So we want to know P. Well, if A is equal to P times 1 plus R over N to the power of NT, then we can rearrange this formula by dividing by all that stuff in the brackets from each side. And that would cancel that out on the right, and it would leave us with a calculation, or a formula for the principal, I should say. Same variables, just rearranged slightly differently. So we could calculate the principal P. Now, we're told that she wants to have $100,000 in her account. So that's A is equal to $100,000. That's not I, the interest, which is great. That means that we should have all the other values that we need. And we're told it's compounded annually. So A is $100,000 over 1 plus R is 0.06. And it's compounded annually, so N is equal to 1. And 1 times the time is 15. Again, be careful in your calculation. One strategy is to calculate everything in the numerator first, and then do 100,000 divided by that, but do whatever method is efficient and accurate for yourself. But after going through that calculation, we get that the total amount that needed to be invested at the beginning was $41,726.51. So that's pretty cool. If you can get 6% annually, you can turn about $40,000 into $100,000 after 15 years. One important note, though, is that this isn't the way most investments happen. Most people don't invest all at once. They keep making regular investments or contributions that build and build and build, adding more savings, earning more interest, and so on and so on and so on. So lots of people choose to take a certain percentage of their paycheck and invest that every week. Other people do it, say, every year or at certain times. But it's not something that you just make a $40,000 investment all at once and then spend all the rest of your money. It's usually a little more complicated than that. But for the sake of our calculations, we're going to try to keep it relatively simple and straightforward. Now, you won't be asked to algebraically solve for R, N, or T in the compound interest formulas. You actually need some pre-calculus 12 level math to solve for some of those variables. So don't worry about that. We're really just going to be focusing on calculating the interest, the total amount of an investment, or the principal like we've seen so far. But theoretically, you could be asked to solve for them graphically. So for example, if we have a graph of this $1,000 investment, you can see that was worth $1,000 at the beginning, and we wanted to know how long it would take for that investment to be worth $3,000, we could look at the graph, locate 3,000, and then trace over and say that the investment would be worth $3,000 after about 22.5 years. So you won't be asked to solve for those things. You might be able to use a graph in certain circumstances to make an estimate of how long it would take, for example.